Hello everyone, and welcome back to an extremely important lesson. Today, we are going to talk about Newton's second law. To start this, I'm going to bring up a hypothetical situation here. Let's say you and a friend go to the supermarket and both of you grab empty shopping carts. You take it into the store and you are planning to race down one of these shorter aisles in the store. On the side, I do not recommend this behavior in a supermarket unless you're planning on getting yourselves kicked out. But we're going to do this for the sake of science. Now, you two are going to race. You're going to start from rest and you're going to race to the end of the aisle. Now, who is going to win this race? If the carts start at rest, that means the velocity of the carts needs to increase. Whoever can increase the velocity of their cart the quickest is probably going to win this race. That means the person who exerts more force on the cart will be the one to win this race because the carts are the same. So let's say this race begins, an eye on my high budget animation here, and let's say that your friend ends up winning this race by about half a cart length. So you decide that you want a rematch. So you both go back to the start, and your friend momentarily walks away from their cart. As they walk away, you notice you happen to be in the canned soup aisle, and you get an idea to help you win this race. And what you do, of course, is take a bunch of canned soup and you stack it in their cart. On the side, I do not recommend cheating either, but again, we're doing it for the sake of science. So you start this race again. Who is most likely to win? Well, your friend won the last race, but you have now changed the situation. The question is, what have you done? Well, you have greatly increased the mass of their cart. So now, even if they push with a slightly stronger force, you actually have a pretty good advantage here to win this race. You literally change the properties of one of the objects in the race, which is your friend's cart. So, winning this race depended on two things. One, how much force was exerted on the carts, and two, what the mass of the carts were. The larger the force, the greater the change in velocity per unit of time. In other words, the greater the acceleration. The larger the mass, however, the lower the change in velocity per unit of time, or the lower the acceleration was. This, in a nutshell, brings us to Newton's second law. The acceleration of an object is directly proportional to the net force exerted on it divided by its mass. Or, put in mathematical terms, acceleration is F net divided by mass. This is Newton's second law, and it is deceptively simple. It is also extremely powerful. This is the single most powerful equation in macrophysics. Everything in the universe with mass, from the smallest grain of sand to the largest galaxy, abides by second law. Everything, and not sometimes, all the time. This equation is both deceptively simple and extremely powerful. So let's bring up a situation and actually put it to some use. Here's a situation I've already set up. In the middle here, I have a force diagram that I've just started. I have a sled. It is on flat horizontal ground. I have a person pulling the sled to the right, which is what this force vector is. The mass of the sled is going to be 50 kilograms. And I have the value for two forces already. Force person on sled, which is this force I have to the right, is 80 newtons. Force ground parallel on sled, which is also known as force friction, is 84 newtons. So I'm going to add those to my force diagram right now. Force person on sled is 80 newtons. Force friction, again, I'm using the abbreviated title here, is 84 newtons. Now I want a full force diagram, which means I'm actually missing two more forces here. The next force we're going to get is the one we talked about last time, which is force Earth on object, or force Earth on sled here. We get force Earth on sled by using the equation we derived last time, which is mass times our gravitational constant, which is going to be 50 newtons times 9.8 newtons per kilogram. newtons cancels out here, which gives me a force Earth of 490 newtons. So I'm going to put in my force diagram. Force Earth on object is 490 newtons. So looking at this, if I wanted to actually make this more accurate for, say, the AP exam, this force should be a lot longer, because 490 is going to be a lot bigger than 80 newtons. In fact, the ratio is still kind of off, but you get the idea. This one going up, this one going up is force ground perpendicular, also known as force normal. Now, the sled is neither flying into the air or digging into the ground. The sled is going to be moving either left or right. So that means force normal is going to be 490 newtons. Something to keep in mind. This can be pretty common in the beginning when you start physics, but do not get in the habit of making force Earth and force normal the same every single time, because there is a number of situations where that is not true. So now that the force diagram is finished, here's what the problem is going to be. This sled is currently moving to the right. I'm just going to say that straight out. So the current velocity is positive 10 meters per second. The question is going to be, what is the final velocity of the sled going to be after a time period of 20 seconds? All right, how fast is the sled moving after 20 seconds from right now? And right now, the sled is moving to the right at 10 meters a second. All right, let's make use of Newton's second law. All right, let's make use of Newton's second law. Acceleration is F net over mass. So looking at my force diagram here, I have 80 newtons to the right, 84 newtons to the left. So I have an excess of 4 newtons to the left, which is a negative direction. My y-axis, however, perfectly cancels. So the net force on the y-axis is 0, which leaves me a net force of negative 4 newtons, because my net force, again, is to the left, over a mass of 50 kilograms. That gives me an acceleration of negative 0.08 meters per second squared. If I now want to get the final velocity, I'm going to use the second kinematic equation, which is my earlier acceleration equation, which is acceleration equals velocity final minus velocity initial over time, also known as change in velocity over time. I'm going to rearrange this to solve for what I'm looking for. Vf equals Vi plus acceleration times time is positive 10 meters per second, plus my acceleration is negative 0.08 meters per second squared times 20 seconds, gives me 10 meters per second minus 1.6 meters per second, because one of these seconds cancels and I get meters per second here, which gives me a final velocity of 8.4 meters per second. So the frictional force on this sled is larger than the force that this person is pulling. Since the velocity is already to the right, that means this sled is slowing down. In 20 seconds, it slows down to 8.4 meters a second. Now, let's do this one more time, except I'm going to ask a different question here. I'm going to give the same initial velocity. So Vi is still positive 10 meters per second. The question is going to be, how much time does it take to bring the sled to a stop? Well, now my givens have changed, so I need to relist them. Vf this time is going to be 0 meters per second because it comes to a stop. My time is unknown. This is what I'm looking for. And the other given I have now is the acceleration is no different. It's still 0.08 meters per second squared to the left. I can actually do this in one shot now. Acceleration, change in velocity over time. I'm going to rearrange this for time. Is Vf minus Vi over A. Vf is 0, Vi is positive 10. So on the top, I get negative 10 meters per second over an acceleration of negative 0.08 meters per second squared. Looking at my units, this is a fraction in the denominator, so meters would cancel when it flips. One of these seconds would cancel, and I would get seconds as my answer. And doing that division, I would get 125 seconds. And of course, my negatives here would cancel each other out, which is an important note. If you are ever looking for time, you should always end up with a positive number. Since positive and negative means direction in physics, if you end up with a negative time, it literally means you went back in time. So if you do end up with a negative, don't just switch it to positive. You need to find out what actually happened in the work to make sure that that wasn't the only issue with your outcome. All right, so this was a demonstration about Newton's second law, how it can be used, and how it relates to kinematics. On the side, that also means I could write acceleration directly like this. I could combine these two quite easily. And in fact, they are used in conjunction very, very often. So it's actually not too unhealthy to think of Newton's second law as the fifth kinematics equation. And yes, I know we have yet to talk about 3 and 4. That will be coming up very soon. That is all for today. Thank you for joining me. This is Mr. M signing off.